without heart. In your head, you're right, but in my head, you are the bad. I wanna show to the world that you're the bad one. You was being bad. That you saw my love, you saw my time, you saw my heart. You begged me to come with you. I don't know, I'm fine without you. You begged me to come with you. I don't know, I'm fine without you. What you do here? Cause I don't love you, boy. I wanna show to the world that you're the bad one. You always being bad. What you do here? Cause I don't love you, boy. I wanna show to the world that you're the bad one. You always being bad. You begged me to come with you. I don't know, I'm fine without you. You begged me to come with you. I don't know, I'm fine without you.
Hello.
Hello. Shall I start, Shubhanil?
Good afternoon, everyone. This is Shubhanil Saha, and on behalf of the Indian Geotechnical Society Silchar Student Chapter, I welcome everyone on today's webinar. So, in our previous webinar, we have received a very overwhelming response, and which has really encouraged us to bring up more webinars. And today, here we are again with another interesting topic. So today we will have a presentation of about 40 minutes, and after that we will have a question answer session, and all your queries and doubts will be answered, and you can ask them in the comment section of YouTube. So please be patient and wait till the end of the presentation. Now, before starting the today's webinar, I would like to give a very brief introduction about our society. Most of you must be aware of our society, but still we have many people who have joined to us today for the first time. So the Indian Geotechnical Society, we all must be aware of it. Professors from many IITs, NITs, esteemed universities and institute of our India, and students, research scholars, and many industry experts are an part of this society. And it has many local chapters across various cities of India. The IGS Silchar chapter is one of those. Now, to encourage the students about the scope and prospects of geotechnical engineering, the IGS has advised every local chapter to establish a student chapter. And hence, on 15th of March 2019, the IGS Silchar student chapter was inaugurated at NIT Silchar. Till now, we have organized many events and activities, like the first one-day seminar on soil foundation interaction, then a field trip to Haflong to study the slope failures and slope protection work, then the PVD installation, prefabricated vertical drain installation works at Srikona, Silchar, and then our first webinar session which we have conducted, where we have obtained a very warm response. Now this gives a very I would like to take this opportunity and share with you all. We have started a new initiative, Omega, online magazine for emerging geotechnical aspirants. It is basically an online magazine where we welcome all the students, industry experts, academians, research scholars to please come forward and share your concepts, ideas, and any topics on geotechnical engineering. And today we are going to launch our first article on Omega, which is on geoform. So for further details, guidelines, and other things regarding to Omega, please follow us on LinkedIn and Facebook. So quickly, I would like to introduce our speaker for today's webinar. We are very glad and extremely sorry. I would like to. I'm extremely sorry. We had a technical problem. So quickly, I would start from this again. So you all must have heard about today's webinar, and quickly I would jump to our new initiative, which is the online magazine Omega. So we welcome all the students, academians, industry experts to please join with us and share your ideas, concepts, and any knowledge regarding geotechnical engineering. For more details, and today we are going to launch our first article, which is on geoform. And further, for more details, please follow us on LinkedIn and Facebook. We will give all the details and guidelines on our social media pages. So quickly, I would like to introduce about our speaker. We are very glad and privileged to say that Dr. Ratnakar Mahajan has agreed to join us again for the second webinar. Dr. Ratnakar Mahajan has vast experience for 13 years across various national and internationally acclaimed projects. He has also contributed to various Indian codal provisions, and I'm sure today we all will be privileged to learn from his boundless knowledge and experience. One more important announcement uh, regarding the e-certificate for today's webinar. This is the link and QR code. Please be patient. This slide will be displayed at the end of the webinar also. So, uh, so please be patient and enjoy the webinar first, and these things will be displayed again. So now, without any further delay, I would like to welcome Dr. Ratnakar to please take this webinar forward. Thank you, sir. Thank you, everyone.
Thank you, Shubhranil. A very good afternoon to everyone. I'm very happy to join you one more time for a next topic that is about the design and construction of machine-made Gabion walls. Uh, so, as Shubhranil mentioned, we will have the presentation for some time, let's say 40-50 minutes. He has introduced me, so I will just move ahead. Before starting the webinar, just like to mention about the organization where I'm working. So Maccaferri is a 140 years old organization, present in 100 countries with 30 factories through 70 subsidiaries. So, Gabion walls. So, first of all, we need to understand why do we need the retention. Basically, if you want to retain any slope or a soil to a particular height, you need some retention here. Now, this retention can be done by number of retaining walls. It could be the gravity wall, or maybe the piling, sheet piling, anchored wall, or cantilever wall. It can be counterfort or buttress wall. It could be crib wall. It could be UCR wall, or it can be a cabin wall. So these are the different types of retaining walls which are available. So as we discussed during the last webinar, India being a very, I would say, dynamic conditions, like especially in the northern part of the country. Now you must be have those people who are from the NCR must have felt the tremors recently. So it's a Indian plate movement happening against the Chinese plate. That's where there are a lot of movements. Hence, the solutions what we are going to adopt are to be flexible. So usually, if we adopt the concrete retaining walls or buttress walls, or let's say relatively rigid structures, there are possibilities of failures if they are combined with moving water. Secondly, the cost of these retaining walls is high. The time required for construction is also high. For example, in concrete retaining wall, let's say you want to construct a 6 to 8 meter high retaining wall, you cannot do a concreting of 6 to 8 meter in one go. You will need to have first the excavation, then the putting the steel, and you do the construction in stage wise, because concrete also you have to do in certain lift. And uh, these rigid structures have very stringent requirement of differential settlements. So in case your soil foundation soil doesn't allow this kind of situations, you need to go for the flexible solutions. So as we discussed last time, earth retaining structures, you have externally stabilized, internally stabilized, and of course in that externally stabilized are the gravity walls. In gravity walls, you have mass concrete, cantilever, and gabions. So these typically are basically walls where you are going to have a filling to be done behind the wall. In such cases, the gabion walls are being used. Now, before going ahead for the Gabion walls, let's understand what are the types of gabions. So, I'm sure you must be aware of the history. If not, I will just briefly mention. Gabions were invented, engineered gabions were invented around 140 years back by Maccaferri in the, I would say, application of riverbank protection. The word was Gabione, and then there was a patent for some time, and then the use of gabions is not limited to only the Italy but all over world. Different forms of gabions have been used. Now, what are the modern forms of these gabion walls? So let's look at from the left to right. The first one is the double twisted, what is mentioned as a double twisted mesh. The material used for making this double twisted mesh is a steel wire, and these gabions can be machine made or handmade. What it means, you can have wires and you make this double twisted mesh. You can make it by machine or by hand. The another type is a single twist. So this is in the photograph you will see the mesh of a single twist. Now this mesh is again made up with the steel wire. Usually this wire is not protected with any additional protection. It's just a steel wire, maybe some galvanization will be provided. Now this can be again machine made or handmade. If you see the fences along the boundaries, typically single twist or mesh is used. That's called as the chain link. Sometimes people use that for making of gabion. The third is the welded gabions. Basically, again, it is made up of a steel wire, and the steel wires are welded together. And with that welding process, you make a mesh like this, a typically square or rectangular mesh opening, and it can be machine made or handmade. Mostly, you will see this would be machine made. The fourth type is basically the polymer gabions. Polymer gabions, there are again varieties like made up of geogrids, made up of rope. So the photograph what you see is the polymer gabions made up of polypropylene rope, and these are handmade where the ropes are being viewed together. Now the question will come now, all these four different types of gabions. So which one what we are going to look in today? So today we are going to look specifically machine made, double twisted, mechanically woven wire mesh gabions. Now, why we are discussing on this but not the others? There are certain reasons. Typically, single twist mesh has a limitation in terms of its strength. At the same time, there are some issues. For example, in single twist, if one single wire breaks, the mesh opens up. Whereas in double twist, if you cut a single wire, still it doesn't open. Now, when you have double twisted wire mesh and welded, so welded definitely you have the wires, steel wires which are joined together by welding, and any differential movements. Of course, these joints will be experiencing some stresses. Relatively, these gabions are double twisted mesh gabions are flexible than these. So wherever you want flexible structures, again welded gabions may not be suitable. The last one is about this polymer rope gabions. Like you know, synthetic materials, they are very good in terms of performance, especially when they are put in the soil or they are kept away from the sunlight. If these gabions are being exposed to sunlight, they will degrade very fastly due to the UV radiation. So these gabions are again not suitable for permanent kind of structures where it will be exposed to weathering actions like sunlight and wind. Secondly, you know, these you can imagine polymer rope gabion, you don't have much stiffness, so it cannot maintain the intended shape. Typically, the box kind of shape, what you can achieve in double twisted mesh gabion or welded gabion, you may not be able to achieve specifically in polymer rope gabion. Also, you may not be able to achieve the same with a single twist gabion. Now, after understanding the type of gabion, it is very clear we are going to talk about double twisted mechanically woven machine made gabions. So, what are the components of gabions? Typically, the first component, the gabion itself. So, this is like number of gabions here. Second is the backfill soil, the soil which you are going to put behind it. Next would be a dotted line. What you see is a non-woven geotextile, which will be acting as a separator and filter. And of course, the material which we are going to put in the gabion. So, gabion filling. And of course, the gabion wall will be resting on certain foundation. So that is the part of it. So let's look at these different components one by one. Gabions, these are rectangular cages made up of woven steel wire mesh, typically as I mentioned double twisted wire mesh. They have side panels, so these are the side panels. Then the end panels, so these are the end panels. Then top and bottom panel, so this is a top panel, and then you have a bottom panel. Diaphragms, diaphragm is provided every 1 meter to separate the number of cells, and then the lacing, basically to join this lead with the sides of the gabion, you need to use a steel wire, that's called a lacing, and the selvage and edge wires. That's what the components of the gabion. Now, this double twisted wire mesh, you know, they are manufactured in many kind, basically different sizes. uh, that way it allows that different field to be used and different strength of the structure can be achieved. So this is what like a double twisted hexagonal wire mesh. Among this, of course, if you load these hexagonal wire mesh, you will find there is a better stress distribution in hexagonal shape compared to, let's say, rectangular or square shape. Now, what are the different mesh sizes of this steel wire mesh? Typically 6 by 8 mesh type, 8 by 10 mesh type, and 10 by 12 mesh type. The 6 by 8 refers to mesh opening of 60 millimeters or 6 centimeter. 8 by 10 refers to this D value of 8 centimeter or 80 millimeters, and 10 by 12 refers to this mesh opening of 10 centimeter or 100 millimeter. Now these gabions are made with a steel wire. So you have a mild steel wire which has a tensile strength of 350 MPa to 550 MPa. The requirement of this steel wire is usually the elongation at break shall be more than 10%. This steel wire is obviously, if you are going to construct a structure with it and it has to be durable, there are possibilities of corrosion. So corrosion protection is provided with a metallic coating. Typical metallic coating is basically galvanization using zinc, or now there are advanced coating of zinc aluminum alloy, that's referred as galvac coatings, which have 3 to 4 times more resistance than just the zinc coating. On top of that, polymeric coating is extruded. So even if the metallic coating of zinc or zinc aluminum, it can also get corroded. So on top of that, that's why a polymeric coating is provided. This polymeric coating can be of a polymer which is flexible, which can sustain the abrasion, which can sustain the environmental conditions to which it is exposed to. That's how you have first layer of protection of polymeric coating, then a metallic coating, and then of course the wire itself. That's how the gabions are being made. Now these gabions, they have certain dimensions, that is the length, then height, and then the width. Typical length of these gabions varies from 2 to 4 meters. This is for standard gabions of 1 meter height. Sometimes even 1.5 meter high gabions are also available, which are typically in 1 meter height. So for 0.5 meter height, typically you will not have this 1.5 meter length of the gabion. 2, 3, 4 is available both 0.5 meter and 1 meter high gabion. So for example, if you look at the 4 meter long gabion like this one, 1, 2, 3, 4, 4 meter long gabion, 1 meter in width and 1 meter in height, it will have four number of cells, 1, 2, 3, 4. So there are three diaphragms which are separating these cells each other. That's what the gabions are. Now, after understanding the gabion, let's understand what is the filling in the gabion to be there. So typically a rock fill is put, where you can have a rock of typically 1.5 to 2 times the mesh opening. So if you have D, that is the mesh opening of roughly 100 millimeters, you will have to have a rock of size 150 to 50. The reason for this size is very simple. When you have rock in this gabion, and if you have rock particle smaller than this mesh opening, definitely the rock will come out. That's why, let's say if it is a 100 millimeter mesh opening, then you will need a rock element which is more than this, typically 150 to 250 millimeters. The specific gravity can be 2.3 to 2.6 depending on the type of rock you are using. And by filling these gabions, it is always recommended to overfill the gabion. So once you go for the filling of these gabions with the stone, let's say this is 1 meter height, you need to fill at least 1 meter plus maybe 1 inch or 2 inch more, so that the lead which gets which is for closing this gabion, you need to have apply some additional stresses or force to close it. That makes that whatever stones inside will be properly packed. Otherwise, once you have a loose packing and you, let's say you finish one gabion, on top of that you put another gabion, then the stones and the bottom gabion will settle and you will not have a very good gabion structure. It will basically deform a lot. That's why you need. Now this is what a general recommendation, but if you see IRCSP 116, it says the minimum rock fill size has to be 1.5 to 2 times the mesh opening, which is what I just mentioned. Tolerance on the stone size, so whatever stone size we say, it can have tolerance of plus or minus 5%. It cannot be more than that. Minimum density 22 kilonewton per meter cube, but this is not again fixed or rigid criteria. In case you are in an area where you don't have stones easily available of this density, then you can use concrete cubes. You may use stones of less density also, because it is a part of design. You use the lesser density of stone, definitely your structure will be bulky. And then of course the stone or the filling what we are going to have must have a sufficient durability, which can be estimated through Los Angeles abrasion value, which shall not be more than 45. Now moving ahead, the next component is geotextile, which is usually placed at the back of these gabions. The reason why the geotextile is placed behind the gabion is simple. When you place the stones in this gabion, there will be a lot of voids. Typically, the voids would be in the range of 30 to 40%. So these are acceptable numbers. Even you can fill the gabions with 50% or 60% voids, but it is recommended to fill between 30 to 40% voids. When you have a lot of voids, there are possibilities of this backfill soil will get washed away or will erode or migrate through gabions and then coming out. To stop that, you need to have a filter here. That filter can be a simple non-woven geotextile. So this non-woven geotextile will act as a separator and filter behind the gabion unit. And this geotextile can be made up of polyester or polypropylene. Usually this geotextile is supplied in the form of roll and this is a small component of these gabion boards. Now after understanding the gabions, the components, the type of gabions which is to be used, let's move ahead for the design steps. So when you design these gabion walls, they are mass gravity walls. So these mass gravity walls are designed by various modes of failure, like you have to check the wall is safe in the overall failure. There is no slope stability issue. The wall is safe in the bearing capacity mode of failure. So your foundation soil has enough bearing, the footing has enough bearing capacity so that there are no settlements and movements. Also, we have to check that the whole wall, if it is a monolithic unit, shall not slide along the base, it shall not overturn, and the most important, this is the part which most of the people don't do it or ignore it, is the internal. So you need to check the each gabion for the compression and shear capacity. So, first step for understanding or designing these Gabion walls, you need to determine the earth pressure. So, obviously, we need to estimate this earth pressure based on the various theories available with us. So, first of all, let's understand if you have a soil element at a depth of Z from top, and if you look at it from a retaining point of view, you have some vertical pressure, and of course there will be some horizontal pressure. This horizontal pressure is usually will be governed by the state of the stress. So typically active state and passive state. When you have retaining wall moving away from the backfill, or the backfill puts a pressure and the retaining wall moves, it can be in active condition. So Gabion walls are very flexible. If there are some high stresses, obviously there will be some movement. So definitely in such cases you can use the active condition. Passive would be like when the retaining wall is moving towards the backfill, a passive condition has to be used. So for the active condition, definitely you know the height of retention which need to be retained. You know the density of soil, then you know the vertical stress, that is the H into gamma, that is gamma H is the vertical pressure acting on the foundation. And then of course you can estimate the lateral pressure by multiplying by a factor called the coefficient of active earth pressure, Ka. Now for coefficient of active earth pressure, there are theories available by Rankine and Coulomb. It is very clear when you go for these Gabion walls, they are not going to have a smooth, I would say, interface between this wall and the backfill. That's why you need to consider the Coulomb theory. This is the Coulomb approach for estimating the earth pressure coefficient shall be applied, where you can assume a wedge at an angle theta, where you will have the mass of this wedge as W. Then you have the interaction between soil and the retaining wall, that's the with the delta. And that's how you do the analysis, and you find out the pressure acting on this retaining wall. Now obviously this is a function of this failure plane, so you can have a number of failure planes and then analyze it. You for your standard analysis or a typical case, you may take 45 plus 5 by 2 and check that. But you, it is recommended you use a software program and then find the maximum pressure which is being yielded by a certain failure wedge. Now, when we are determining this, we need not to just consider the soil weight, but we need to consider the phreatic surface. If your uh, retaining wall is going to be waterfront, or you are anticipating lot of water coming gushing through this wall, then obviously you need to model the phreatic surface. So let's say if it is a waterfront structure, you know the water level. You can assume some maximum water level depending on the high flood level, and then do a modeling of the phreatic surface and do the analysis for the effective stress condition. On top of that, of course, you need to consider the surcharge loads, which could be the, let's say, if it is for road, it could be the live load from the road, typically 24 kPa. If it is railway, you will have to refer the railway guideline, but roughly 60 to 70 kPa you can consider. If it is for building or some other application, let's say car park of the mall or something, accordingly you can consider the live load. Any concentrated load on top of that you need to consider while doing the analysis. Of course, in addition to that, India being seismically active, you will need to consider the earthquake loading. So you can refer IS 1893. India is being divided in four different zones: zone 2, 3, 4, and 5. According to the zone, you can decide the acceleration and apply. For analysis of these walls in the seismic condition, you can use the pseudo-static method. You can go for Monocabe method and determine this earth pressure acting on it. So let's look at the different modes. Let's say the sliding. So we assume this whole retaining wall will act as a rigid body and it will slide at the base. So for that, of course, you need to know the active thrust, passive thrust, wall unit weight, normal pressure at the base, and the resisting force T. So definitely you can take a ratio of the stabilizing force versus the disturbing force or the sliding force. This is how you can do the analysis for the sliding chase. It is very simple, not very complicated. Definitely the resisting force here would be the resistance offered at the base because of the interaction of the gabion and the soil together, and the driving force would be the active earth pressure or active thrust. Obviously this resisting force is a function of the weight, mu w is equal to mu tan phi, mu basically mu is equal to percent friction of fraction of the tan phi value. So w tan phi into mu would be the resisting force. Now, the next check is about the overturning. You can assume that this whole body is a rigid body and there are some forces acting on this wall, typically earth pressure, and you consider rotation of this retaining wall at the toe and do the moment analysis. That's how you can do a stabilizing moment by overturning moment. You do the analysis, you will get the factor of safety against overturning. Next is about the pressures. So when you construct these Gabion walls, it is going to exert pressure on the foundation. Usually, you can typically use maybe Terzaghi theory or any other theory you want to use for it for determining the bearing capacity. As this retaining wall is going to be long enough, you can consider the footing as a strip kind of footing. The parameters for the foundation soil has to be considered. If it is a layered soil, definitely you will need to model the layered soil in software, or if you are doing by hand calculation, you will have to use your engineering judgment whether to use the soil properties of layer just below or do arithmetic mean of different properties depending on the site condition. So here, for doing that, of course, we need to keep in mind that the design shall be such that never the wall shall experience any tension. So it's called no tension analysis. For that, the middle third rule to be followed, that the resultant shall follow within the middle third of the Gabion. And for that, obviously, we can follow this equation, that is normal load by width into bracket of 1 plus 6 e by, where e is the eccentricity between the center line of the foundation and the where the resultant is acting. Then moving ahead about the slip surface analysis, there are a number of methods available. You can choose anyone, whether it could be Jan Boo's method, it could be generalized equilibrium, or anything. I recommend you to do a Bishop's analysis. It is quite simple and quite accurate compared to other methods. Like, there is not much variation between the factor of safety analyzed by Bishop's method or the generalized limit equilibrium or other methods. So here you consider some center of the various rotation, and then you have a circular arc where you divide this whole mass into the number of slices, and you do solve this equation of Bishop's, and you finally you get the factor of safety for the global stability. The most important part, as I mentioned, is the internal stability. While analyzing these Gabion walls, we seen the sliding, bearing, overturning, and global, which is common for any kind of retaining wall. Like in RCC, we will do a steel design or concrete design, but in Gabion wall, there is called the internal stability because of the soil and the soil pressure and the self weight. Each layer of the Gabion will experience some compression and shear. So due to the soil thrust and surcharge load, we need to check the shear and normal stresses. Typically, let's say tau, which will be the T into act or width B, let's say it is acting, that will be the tau. So this we have to ensure that this is within permissible values, and the normal pressure sigma will be N by 2D. So this is the normal pressure acting again over the effective width of this Gabion at that layer. We need to again check whether it is within the permissible limits of the Gabion. So how do we determine this? What is the permissible limit for the Gabions? How much the Gabions can take the compressive load? What will be the sigma admissible? How much would be the shear capacity of the Gabion? So research and development was taken by Maccaferri around 1970 79, where the first phase was compression and shear test, and second phase was on the full size retaining wall. So the aim was to determine the strength and deformation parameters of the Gabion, verify the first phase results, and establish most appropriate calculation parameters for the limit of application. So here full size Gabions were tested for compression and shear. So this is what you see, a Gabion double twisted wire mesh, which is formed as a Gabion in which the stones were filled and they were compressed under compressive stress. And of course, this is a shear test where we are applying a load here, and there is a shearing happening at these two edges. So this is the first phase of the test where the compression and shear was done. This is a full height retaining wall was built. Here basically a membrane was put and water was completely filled till the top, and then the deformation behavior of the Gabion was observed, and accordingly the parameters were ascertained. In addition to that, the test on the mesh were performed, like the tensile strength of mesh, so holding the mesh in a UTM and doing a tensile test. Then the tensile strength of the wire itself was performed, and the punch strength of the wire was performed, or the mesh was performed. So the results showed that gabions are ductile. They are not brittle. They deform. They give you enough indication before failure. So that's what one observation. The gabions can withstand a normal load of 300 to 400 ton per square meter, and the modulus could be 25 to 40 ton per square meter. And more or less we observed the shear is the cause of the deformations of the gabions. The most important part when we do this analysis, we require usually two parameters, that is the cohesion and the friction angle. So you can imagine, if you have stones and you try to stack these stones like this without the gabion, they cannot be stacked. Now with the gabion, you are able to make a vertical shape here. So that means there is some overall cohesion effect being added to the stones. Otherwise, they could have been in a triangular, I would say, pyramid shape, and that angle could have been the internal friction angle of the rock itself. But now with effect of this mesh is encountered, or maybe considered in equation form, which is given here, where it is related to the mesh weight per cubic meter of wall, and that's how it is being done. Similarly, the internal fictitious angle of this gabion and the rock together was determined, which is related to the density of gabion. This is the formula. Now keep this in mind. Whatever this testing is done, that is based on some wire mesh produced by Maccaferri and being tested for certain parameters. So obviously these parameters, what you see, is applicable to the gabions produced by Maccaferri, and you can imagine the kind of extensive research was done based on the compression test, full wall monitoring, the behavior, and the other parameters of the mesh. And you can use these parameters in the your analysis for doing the internal stability. Of course, these are the recommended factor of safeties as per IRC 116. Before IRC 116, there was no one document which could give all kind of factor of safety. There is one IS code which gives these factor of safeties, but IRC 116 is a latest one, where let's say for global stability, for static case it could be 1.3, seismic case 1.1. If you are using these walls for directly bridge abutments or building, you can increase the factor of safety to 1.5. When you check for sliding, it could be 1.5. In the static seismic 1.125, overturning 2 and 1.5. For bearing capacity, if you are considering for walls, it could be 2 and 2.5 for abutments or buildings or important structures. Internal stability 1.5. For seismic case, of course, again it is 1.125. So this is the target number of factor of safety which you can target for this. Now, after understanding this, how to analyze these sliding, bearing, overturning, as well as global and internal stability, some points we need to remember that you can have the walls stepped out or stepped in. Typically, when you are going stepped in, it is recommended to have a 6-degree better. When you are providing gabions, never provide gabions of irregular wall rear surfaces. For example, if this is a gabion of 2.5 meter, on top of that, you again put a 2.5 meter with offset on the back side. This is not good practice because there will be some additional stresses coming on this gabion with this because of the soil pressures, and the behavior would be different. So avoid these irregular wall surfaces. Sometimes people tend to stack the gabions just over one each other. That means you have 2 meter gabion, you stack over top of each other, making it 80 degrees. So this is not a wall. This is just you are putting some kind of cladding, and this is not the conventional retaining wall. So do not consider this as a retaining wall. It's just a fascia or a cladding you are doing. While providing the non-woven geotextile, sometimes people tend to provide the filter at the bottom also, but here it's not really required. Typically for normal retaining walls, you can provide just the filter at the back. If there is a moving waterfront structures, and in this portion that is in front of the wall, any protection you are giving, that there you can provide the filter, but usually you don't require this non-woven geotextile at the bottom. The reason for it, the moment you are introducing a filter between the gabion and the soil, there is a reduction in the friction between the gabion and the soil. So here there will be reduction in the resistance because the friction between the gabion and the soil will be reduced, presence of geotextile, and your structure will become very bulky from sliding point of view. While modeling the groundwater, of course, you have to model, let's say this is a stagnant water you are encountering. So here it is better you model the fluctuating water level, as well as accuracy of the water data is important. Fluctuating means the critical condition would be you have water level outside the wall lower, and the phreatic surface at higher elevations inside the backfill. This would be the worst condition, so you can model that. While checking the overall stability, of course, you need to consider what are the slope inclinations in front of the wall and the back side of the wall, and then you check the overall stability. Sometimes people have a tendency to use a kind of a shear key or foundation key at Gabion foundation, but this is not required. If you require something to optimize the foundation, instead of providing a shear key like this, you provide a little wider base with a projection on the back side, and that is toe and heel side of the Gabion wall. This would be fine. If you intend to provide a very long base of the Gabion, and you have only this wall, this condition, this is not going to serve the purpose, because the load distribution typically will happen in 45 degrees, and the rest of the part of the Gabion will be west. It will not be much useful. So don't extend these bottom units too much beyond. Let's say if it is 1 meter height, you can go for 1 meter backside, not 2 or 3 meters that way. When you are encountering the waterfront structures, you will be required to protect the wall from scour, because over a period of time there will be scouring happening, so you will need some embedment. So usually designer will have an option of go deeper and provide a deeper foundation, or alternatively you can have a shallower foundation but you provide a apron in front. This would be cheaper, this will be easy to implement. We recommend this kind of option rather than going deeper and creating a lot of instabilities and difficulties in construction. Now, whatever we discussed about the design, what are the codal provisions? So you can note it down. IRCSP 116, it talks about guidelines for design and installation of Gabion structure. It is published in 2018. This is very good document. It covers not just Gabion retaining wall, but it covers the apron design, the use of these Gabion structures for erosion control, typically in the rivers. That also it covers. IS 14458 Part 2, retaining wall for hill areas. Here guidelines part design of retaining and breast wall. So here some portion of design of Gabion walls is covered, but IS 116 is detailed. IS 16014 is the standard which gives about the material specifications of Gabion. IRC 89 is the latest standard where it talks about river training and control works for bridges. Here again, the standard deals with various solutions including Gabion. MOTH Orange Book section 2500, section 700 covers these products. 2500 specifically for river training and protection works. IRCSP 113 for flood disaster mitigation, which includes again use of Gabions for different applications. IRC 34 road construction in areas affected by waterlogging or flooding. There also the use of Gabions is covered. IRC 56 recommended practice for treatment of embankment on roadside slope erosion. Here also the recommendations for use of Gabions have been given. Now, after understanding design, after understanding codes and what is to be done, the question comes: how much is the carbon footprint of these structures? So, let's say if we consider the Gabion walls versus a concrete wall, detailed analysis is performed from the material manufacturing, that is wire being manufactured, it is shipped to the plant for making the gabions, then it is shipped to site and being installed. Same for the concrete wall. So the quarrying of the lime and then processing of that lime to becoming a cement, the crushing of stones, transportation of that to the construction site, making concrete and putting in place, including the steel inside the concrete wall. So if we do this calculation and if you find the emission of carbon for the concrete wall versus the Gabion wall, so you will see here a very high carbon emission, around 50,000 kg CO2 of equivalent is being emitted for a concrete wall. And if you consider the Gabion walls, where you have stones to be brought from more than 100 kilometers, still the emission would be less than 10,000. And if the stones are very nearby, it is even less than that. So here the blue part is the red part is basically transportation CO2 emission. So overall, it is 80% less carbon being emitted by using these walls. So that's why these retaining walls are environmental friendly, because they are emitting less carbon compared to the other kind of retaining walls. Now let's look at the construction step. So I will just take you to the one animation where I am showing some construction steps. Okay. Okay, so for the construction steps, let's say the first step is about the Gabion bundles. So you receive these Gabions in the form of bundle, and they are color coded. Different sizes are there: 4 by 1 by 1, 3 by 1 by 1, 2 by 1, something like that. So you will receive these Gabion boxes in a folded form at the site. Before you start the construction, you need a lacing wire, you need wire cutters and pliers, you need a wooden rafter, you need the hand gloves, a lead closer. If you have the lacing wire, you don't need mac ties, or if you have mac ties, you don't need the lacing wire. Same is with the rings and fastener. If you are lacing wire, you don't need these rings and fastener. Automatic fastener tool and manual fastener tool if you are using these rings. If you are using the lacing wire, just pliers is fine. So in India, mostly the lacing wire, pliers, wooden rafter, gloves are enough for working. And of course, for protecting your eyes, you need to wear goggles during the uh, construction of these Gabion walls. So first, whatever the Gabion you receive in a folded form, unfold it, put a wooden rafter below it, and then remove the fold. You will have the end panels, top panel, bottom panel, side panel, and lead and diaphragms. This is what the Gabion would be. Then you assemble this Gabion, make the sides together, At the edges you have extra wire, you can just twist it and you can make this Gabion mesh in a box form. Then you have the tying of these side panels together by lacing wire, typically in the double and single fashion. So you have a steel wire, you take a two turns and then a single turn. So that's called as the double and single turn pattern. Okay, and then you join these boxes, you join the diaphragm and join the two boxes together also with the same process. That's called as the lacing procedure. If you are not using the lacing wire, you can use the simple clips is the alternative. After that, your boxes are ready. You can put multiple boxes together and join them. Then you bring your stone depending on the mesh size. As I mentioned, 150 to 250 millimeters. Fill this Gabion to roughly one third height. If it is 1 meter high Gabion, you fill it up to 0.3 meter like this. After finishing the first one third layer, then sorry, I will just go back. Okay, you put this uh, after that you can go this process by filling, but keep in mind while filling you have to follow certain process, like you cannot have this box complete empty and this box complete full. If it is done, the diaphragm here will deform. After first filling of 0.3 meter, you need to place the basically called as the stiffeners. So you can place the additional wires here and then go for next one third and next one third. That's how. As I mentioned earlier, you need to overfill these gabions roughly by 20 to 40 millimeters so that there are less move deformations happening in the gabion wall. Alternatively, you can use steel wire to make these kind of ties. Same process, and then fill it. So you have a retaining wall. You have one box here. You have another box. You can join them together. Fill it with stone. Have the bracing. Fill it with this. Then the next wire, and then you have a geotextile. Then you put a soil in number of layers. Then compact it. Then Gabion. Then compact it, then fill in Gabion, then it shall not happen that you make full Gabion and then you put a backfill later on. If you do like that, your Gabion wall will rotate. It is always recommended you fill the Gabion with stones first, 1 meter, then put the soil, compact it, then you have the next Gabion, next Gabion. That way you need to proceed. So this is very simple method of the uh, filling the Gabions. Let me go back to our presentation. Okay. Okay, after construction steps, let's understand some case studies. As the time is limited, I will not be talking on case studies much because there are a number of case studies all around the world. We started working around 140 years back. Maybe thousands of structures have been built worldwide. I would like to show you very few selected case studies. So this is one of the case study along Mumbai-Pune Expressway. Here the scope was improvements and widening of existing guard section on NH4. So you can see the Gabion walls being. The reason for adoption of these Gabion walls in Mumbai-Pune Expressway was it was passing through these western ghats, and then you have the stones which is coming out from the excavation, and the stones were used to fill the Gabion itself. So that's how. And the this is the first expressway in India, and these retaining walls are performing very well since then. And this is very good example of even though we are saying it is flexible structure, even these can be used to support the rigid pavement kind of structures also. It's a matter of how you design the walls, how you construct the walls. These walls can behave really well. The another example of Konkan Railway, Konkan Railway established rail track from in the Konkan region, from passing from Mumbai to through Goa to Kerala, and the terrain is very treacherous. It passes through lateritic zone where the soil is strong when it is dry, but when it gets wet, lateritic soil, when it gets wet, it loses its strength, and Konkan Railway face number of slides during monsoons. So one of such slide was treated first with the Gabion walls, and this photograph you will see there are no Gabions present. The structure is so beautiful that the Gabions completely gel with the environment. So this was the wall before, just after the construction, and this is how it is completely blend with the environment. Being the porous kind of material, it allows the water to be drained very easily. That's why these kind of retaining walls are preferred where you have heavy rainfall, challenging soil conditions. Another challenging soil condition, this is a project from Maharashtra, Nashik. Here, along the river Godavari, a retaining wall was to be built. The soil conditions were not good, very poor soil, roughly phi value of something like 20 degrees, very low cohesion. Here the Gabion walls were built, and you can see this is during construction, this is the after the construction in the year 2003, and this was roughly I think year 2010 or 12, something like that. 10 years after the construction. Very beautiful Gabion walls merging with the environment. Like this, in Southern Railway, number of Gabion walls have been built. Extensively, railways have used these Gabion walls, especially areas of heavy rainfall. So it's not just Himalayas, but it has been used, let's say, from north of the India to complete south of the India, extensively east to west. Very beautiful Gabion walls have been constructed. There's another project from southern part of country, Gabion walls for these landslide stabilization or slip stabilization. So overall, if we see, there are four different paradigms. These Gabion walls are flexible, and basically they are structurally continuous. So if we see the rigid structures, typically you say concrete structure, when there are moving water, there are possibilities of failures. But these flexible structures, porous, easily allowing the movement of water, they stand against erosion. Undermining is definitely being controlled by providing proper uh, aprons, and these structures can tolerate settlement without damage. In rigid structure, the failures could be sudden. So like this, if there is a erosion, these are flexible material. It can adopt or take the shape of the eroded surface. They have very good filtration and permeability. So the water can easily enter in the structure, and easily it can come out of the structure. It's so permeable, and there is a natural exchange of the surrounding environment and filtration of groundwater. And usually we have found these gabions after a few years, if it is very good environmental condition, it will be completely gelling with the environment. You will have a lot of vegetation coming. Okay, the next is filtration and permeability. This is what we discussed. After that, the durability. These materials have typically, as I mentioned, metallic coating in addition to a polymer coating. So for very high aggressive conditions where you have a lot of rainfall, let's say if I talk of the wettest part of the earth which is in India is Cherrapunji. Even that area you can use this, because the polymer coating will control the corrosion, as well as there is additional metallic coating. So usually if you use the zinc aluminum alloys with polymeric coating, you can have a life of roughly 120 years. Of course, you can use for the medium and high aggressive condition. Depending on the atmospheric condition, we can choose the different coatings. Some example of durability, this is the project from Italy, realignment and bank protection along Tenna River in 1922, and this is in 1950. And the examples of the realignment of canals in 1971. This is projects in USA from 1974. Then the last, environmental friendliness. These structures are environmental friendly. The Gabions and renovators easily integrate with the natural ecosystem and provides a sheltering effect. Being filled with stones and you have voids, the soil can get easily deposited here, and it is favorable for the environment and recovery stage. So this is the structure built in 1955, and this is in 2010. Now you cannot see any stones there. Even like this is an interesting case where you have the tree coming from the mattress itself. So this tree trunk has completely, the mesh is engulfed in that. So it is completely fully integrated with the environment. So in summary, these structures are low cost elements, very simple and efficient to install. No specialist workforce is just no skilled manpower required for these given walls. They are economical compared to conventional retaining structures. They are faster in construction. I would say they are all weather kind of materials. You can use these gabions during monsoon also for the construction. Like in concrete, you cannot do it during rainfall, but gabions you can do that. Once they are nicely filled, aesthetically pleasing structures will be basically achieved. And if we use proper tested material, this will help in performing the building the structure of performing required design. Number of people have mentioned to me over these last 13 years, gabions are failing here, gabions are failing there. I always tell them, have you installed the structures as per design, and is the design correct? After that, whatever parameters you considered in the design, are these being used in the field? So for example, whatever parameters for internal stability I showed, do the gabions which are being used have these parameters? You cannot just use any gabion and use some other parameters to design. That relevant parameters has to be used. This design is of Gabion walls is nothing but like similar to mass gravity. In addition, you need to do internal stability checks, that is the shear and compression, and that's how you can ensure the proper designed structure. With this, I would like to thank you for patiently listening the talk. And now I hand over to the organizers for the next question answer session. You can note down my email address r.mahajan@maccaferri.com, and these are the details of IGS student chapter, IGS Silchar students at gmail.com, and LinkedIn and Facebook. Thank you very much.
Uh, thank you, thank you, Ratnakar sir. This was a really wonderful presentation. It was very informative and insightful, and I am sure today all the viewers must have learned many things from you. So this is the link for the certificate, and you all can take this from here. And sir, would you like to attend some questions, address some questions now, or should we
I
email
will.
all the questions?
I think I will take few, let's say 5 to 6 questions. Let me just go to the live comments.
Okay, okay.
So
So,
I think
uh,
shall I go ahead?
okay, sir, please go ahead with some questions.
Okay, so the first question is from Prathamesh. Why to use specifically only steel wire in Gabion? What if aluminum or any other material is used? Uh, you are free to use any kind of material. It's I would say the choice of the person, but the steel being very old material, knowing the performance and the cost, definitely it is the material. But if you want to use any different material, it's fine, you can go for it. Mm. Uh, The next question is from Mr. Praveen Kumar. Why don't we fill Gabion with other materials like broken bricks, concrete, waste material? Very good question, Praveen. And yes, it's not always to use rock. As I mentioned, if rock is not available, you can use other materials, like as you pointed out, bricks or other waste materials. Of course, the requirement would be the materials must have proven durability, or you must have a material which is having some durability. For example, We have used the specially made stones out of the industrial waste. We have used the concrete blocks, so you can use different materials as the filling material. I hope I answered your question. Uh, okay, the next is the question is from Zaman Amir. Can you have more explanation about geotextile? Okay, geotextile is a filter material to be placed behind the gabion. The purpose is to separate the backfill from the gabion voids. So here the function is separation and filtration. Filtration means where you are going to allow the movement of water and holding the soil particles. So there is a specific design of the geotextile filter that is to be followed. You can refer ASHTO, or you can refer IRCS 59, you can refer IRCSP 116 for understanding more details about this geotextile. The question is from Dibyanshi Das, sir, what will happen if we apply tolerance on size of stone less than or more than 5%? Of course, the reason I explained earlier, if you have very small stones, the mesh has some opening. The stones will come out of the mesh, so you will lose the stones. If it is too big than the sizes being mentioned, so you will not be able to achieve the void ratio what I mentioned, because you understand the design of these Gabion walls is completely based on the mass gravity principle. That means the self weight of the Gabion will resist the sliding, will resist the overturning and this kind of forces. If you increase the stone size, you will not have enough packing, you will have a lot of voids, you will have less density. That's why, and there will be a lot of deformations in the Gabion. That's why the size is being recommended. Okay, the next question from Ishan Nagar, sir. What is the main disadvantage of Gabion apart from its cost and manpower? And as I know, were built in military purposes too. What are the aspects you suggest to make more strong? Uh, Gabion doesn't have a disadvantage of cost. Gabions are actually economical, and manpower, again, it's not disadvantage. As I mentioned, you don't need a skilled manpower, you just need people. You train them initially for 2 3 days, and common people also can do Gabion walls. It's very simple technique. It's just matter of following some basic rules, which I had explained, like during construction, how to fill the stones, how to compact the soil, how to proceed. If we follow that, so, and Gabions are strong enough. I don't think there is any need to make them stronger. Uh, there is a next question from Piyush Das. How Gabion wall will help in sliding of rocks? Sliding of rocks, I'm not sure whether you mean by the slope stability. If you're talking of a slope stability issue, then definitely you can provide the toe walls and do that. The next question is from Bikram Parida. Please mention that the disadvantage of Gabion. So disadvantage of Gabion, I don't think any such disadvantage, but of course, as I mentioned in the beginning, these walls are used for field purpose. So when you are going to fill the soil, you use this. So definitely this cannot be used for a cut slope stabilization. There you will need some different techniques. I would say that is not the disadvantage, but that's the area where you can use these Gabions. Uh, of course, if you want some structure which is completely rigid, you don't want any deformations at all, definitely the Gabions cannot do that. So again, it's a Gabion main advantage of flexibility is there. So that this kind of things are there. But other than that, I don't find anything. Kumar, next question is from Kumar Shubham. If a Gabion wall is present near water body like pond, backfill site, in what case should use the filter at base? If you have a movement of water, then only you can use, but even at that case also is not required. Basically, in front of the Gabion wall, if you are providing a apron, then you need to provide the geotextile rest. The next question is from Charmi Joshi. How Gabion wall construction is advantageous or RE wall construction, having extensive reinforcement and precast concrete panels. So, Chami, it's like the gabions typically, as I mentioned, it's just stones and the gabions cages, very easy to construct. Whereas in reinforced soil wall, you will need to cast the concrete panel, you will need steel in that, you will need some machinery. Whereas in gabions, you just need compactor and rest of the things are done. Definitely for higher heights beyond 6 meters, the reinforced soil walls are economical. Gabion may not be economical, and as you go for very high heights, it the Gabion wall base width will be very high. You will be handling too much stones over it. Okay, so Shubranil, I think rest of the questions we will take it up and answer them over email.
So thank you, sir. Thank you for this question answer session. So I know a lot of questions are left. We will try to select some good questions from here, and sir will answer them, and we will send them to everyone to their email address.
Uh,
Okay, now I would like to take this moment to share our next event. So next on 10th of June on Wednesday, we have a session. This time we are not doing a technical session. It is by Dr. Dhubad Tipal from Silchar. So he will share some advice and some SOPs. So how and strategies how we can live with this challenging novel coronavirus. And then again we have our dear Ratnakar sir on June 12th. And again we will have Dr. Arjun Sil, Assistant Professor of MIT Silchar. Hello. So on 12th of June, we have on 12th of June we have again Dr. Ratnakar Mahajan with us, and 14th of June we have Dr. Arjun Sil, Assistant Professor of MIT Silchar. So we have many exciting topics coming up. So please be with us and follow our social media handles for further updates. So this is the so I would like to conclude for today's webinar with this. Thank you again, Ratnakar sir, and thank you everyone for being patient and be with us. Thank you. Hello. Am I audible now? Hello everyone. Is it sorry for there is some network issues. I would do it again. Am I audible now? Hello. So I'm really sorry about this technical issue. So I would like to announce our next events. We have a webinar on 10th of June, morning 11 a.m. By Dr. Dhubajyoti Paul. MD from Silchar. This is regarding the COVID-19 and the strategy. How can we live with this COVID-19? As we all know that till now it is not eliminated properly, and we have to get back to work in our normal lives again. And again, we have our dear Ratnakar sir again on 12th of June, and we have Dr. Arjun Sil, Assistant Professor of NIT Silchar on 14th of June, 11 a.m. And again, we will come up with more exciting technical webinars. So please be with us and follow us on our social media pages. So thank you everyone. Thank you for being patient, and sorry for today's technical problems.